Good morning, guys. I'm Mr. Rose, and today we're going to explore two AP problems. And as you can see, I am doing this from an empty jury room at the moment. So, the first problem, as you see here, they gave you this platform and they gave you some information. They said this little wheel was rotating that was spinning the platform. They said it started at rest. So here, the I of the platform, that's IP. The moment of inertia of the platform is given as IP. It starts at rest, 0 radians per second. It eventually gets up to speed at a final rotational velocity of omega p. And the wheel is giving a constant force. They told us that F perpendicular because the wheel was perpendicular to the platform. That'll come into play later on. And our first, they also said there was no slipping, so I wrote that down. Our first portion was what is the angular speed, omega p, when it gets to its full speed, but they wanted it in terms of these variables. So I started with our kinematic equations. It seemed like a good place to start. And I said, this is easy. I got this, except I've got this term alpha here, and I can't have it in terms of alpha. So I need to get rid of alpha. How do I get rid of alpha? Well, I know F equals ma. I also know torque equals I alpha. And since I have an I may as well try and apply that. So I say torque equals I alpha, where I know I is the I of the platform, but I cannot be in terms of torque. So I can't just say tau over I is alpha and plug that in because torque is not given here. So I need to look at the other side of the torque equation, and that is the FD cosine theta. I told you that the constant force perpendicular will come into play. That comes into play here because it's FD cosine theta, where theta is 90 degrees. So my torque is really just FD. You can see I labeled my equations here, 1, 2, and 3. So now I'm going to combine equations 2 and 3 to say my force times distance is equal to the rotational inertia of the platform times alpha. So I know alpha is FD over I platform. And those are all things I can be in terms of. So now I just plug that back in. I know I started at rest, so I know the final rotational velocity of the platform, omega, is FD delta t over the moment of inertia of the platform, IP. So B was a little bit easier, just a little bit of algebra, where we're solving for the kinetic energy. Kinetic energy, we know of the disk when it's at speed, so it's at its final rotational velocity is 1/2 I omega squared. I was given, and we just solved for omega up here. So I take this FD delta t divided by the moment of inertia of the platform, and I sub that into my omega squared. So make sure you square it and make sure you square it correctly. That's really the only place I could see a mistake here. Lots of things cancel out. Again, in the terms that we're looking for, I have kinetic energy in terms of force. Distance, that is a delta t squared. I was very specific because they actually said delta t over the moment of inertia of the platform, 2 of that, or 1/2 times that whole thing. The next was a little bit tricky, the angular speed of the wheel. So that was the angular speed of this little guy. We know the angular speed is obviously different than the angular speed of the platform because they have different radiuses. This had a radius of big D, the wheel had a radius of little r. But where those two things are in contact, as the wheel is turning and the platform is turning, their tangential speed, V, you have to recognize that those two things are the same. So the velocity of the wheel is equal to the velocity of the platform, and we know velocity is equal to omega times r. That's my general form. I'm not trying to say that little r of the wheel. Obviously, it is the little r of the wheel, but in general, it's just omega times r. So here I have omega wheel times the radius of the wheel, omega platform times the radius of the platform, which was given as a d. I know that's a little confusing. So I know that omega wheel is just the omega of the platform times d over r. You did not need to sub out all of this for the platform. It was not necessary. So again, omega wheel, omega platform, radius of the platform, radius of the wheel. But now it got a little bit not really tricky, but this is the first time we started talking about moment of inertia. Not moment of inertia, I'm sorry, angular momentum. So we're going to remove the little wheel that was spinning and get the platform to go, and they're going to drop an identical platform. Now, right away, if it's an identical platform, you should be able to say, hey, I bet you the final velocity is half of the initial velocity. That makes sense, and that's kind of what we're proving here. So you can almost think of this as an inelastic collision. It's really not, but we have the initial momentum of the platform spinning. We're dropping another mass on it. So the speed has to slow down, but the total momentum, in this case, the angular momentum, has to be conserved. So we have the momentum initial equals the momentum final. Here is the initial momentum, which is the wheel when it was at speed. Here's the final momentum. Notice I have 2 times the moment of inertia because the discs are the platforms are identical. So IP, that's angular momentum, is I omega. Angular momentum is I times omega. And then from there, it's just simple algebra. And again, it should make sense that the angular velocity, the final of 2 disks, is equal to half of the initial because it's got twice the mass. All right, now here is where it started to use the graph. Now, full disclosure, I cheated. I did not copy the graph onto a piece of paper. I did not print it out. I literally just took a ruler, slapped it on the screen, and said, this looks like the slope of my line. They gave you the points. It looked like a pretty good graph, and you might not know why you need to take the slope, but again, we're always taking either slopes or areas under the curve. That's what we're doing. So I'm looking at this saying, hey, I'm probably going to take the slope or maybe the inverse of a slope. I don't really know. So for part 1, I literally just put my ruler, like I said, on the screen. These are the points I took from the graph. And I said I had a slope of 0.467. And my slope was the final velocity over the initial velocity, because that was what my graph was. Omega final and omega initial. Part B, this part was hard, or Roman numeral 2. What we were looking for Roman numeral 2 was the moment of inertia of the unknown item. So we're looking for I unknown right there. So same thing, I'm using conservation of momentum because it's a law. We can always use conservation of momentum. Since things are turning, I'm using conservation of angular momentum. So here I have my initial momentum equals my final momentum. And this is, they gave us some momentum of the moment of inertia of the platform of 3.1. That's going to be important. So here I said I platform, which I know, my initial rotational velocity of the platform, which again I know, is equal to my final momentum. So I have 2 objects, not identical anymore, 2 objects on top. That's what we have here. Moment of inertia is we just add similar to mass. So platform and the unknown times the final velocity. Now you might be able to see why I took the slope of the line. Look, slope of the line, omega f over omega I. So I'm looking at this, I want to get omega f over omega I. So that's what I arranged. My final rotational velocity, my initial rotational velocity, and I set up this proportion. And now I have something that is full, I know everything. I know the ratio here. I know my moment of inertia of the platform. I know the platform. I can solve for the unknown. I do a little bit of algebra like that, the moment of inertia of the unknown. I plugged in my values, and I got a moment of inertia of the unknown object of 3.54 kilograms times meters squared. Last bit, we needed to compare the initial kinetic energy to the final kinetic energy and come up with a reason. Now, you know the mass is going up, and we know kinetic energy in theory, like linear or translational kinetic energy, 1/2 mv squared. So you might think right away, mass is up, moment of inertia is big. Maybe that has to be a higher kinetic energy. But in this case, our kinetic energy is less. Why is our kinetic energy less? Well, even though our moment of inertia is higher, right? Just like if I'm running down the hall and I pick up more mass, I get more mass, but I slow down considerably. In this case, the disk slows down considerably, such that that velocity, or that omega squared, is a bigger factor. So the final kinetic energy has to be smaller than the initial kinetic energy because the velocity increases, because of the comparison of the velocity. The velocity decreases, thus the kinetic energy is going to decrease. You know what, I'm going to do number 2 in a second video just so they're not so long. So that's all I have for you here today. If you like this video and you happen to be on my YouTube channel, feel free to like, click, or subscribe, and you will see me next time.